So, hello everyone. So, next we'll go to another concept, that is the stresses that is generated in a chain link, and we'll solve a problem on the chain based on chain link. So, coming to the concept that is the stresses in a chain link. So, you must have seen chains normally, which are the multiple number of links which are generally used for hoisting purposes and all. So, we'll consider one particular such link and we'll do the study to understand what will be the stresses that are generated at the inner as well as at the outer surfaces of a chain link at two different sections. Let's say at section BB and section AA. Okay, so a chain link or a link itself basically consists of, as you can see, it has it has two semicircular shapes. It has two semicircles, one at top and one at the bottom, and it is connected by two straight portions. Normally, this is the cross section of a link. So, multiple links are connected to form a chain which is used for a hoisting purposes and all. Okay. So, here as you can see, this is a semicircular shape, and similarly, a semicircular shape is at the top, bottom, and these two are connected using a straight portions. Okay, and as you can see, the chain link is subjected to a tensile load. It is subjected to a tensile load. So you can see will be considering a section BB. We'll be considering a section BB, which is at theta is equal to 0. That is, section BB is theta is equal to 0, which is acting along the line of action of load. So the moment generated in a chain link at section BB at theta is equal to 0 is given here. This is the expression for the moment generated at section BB along the line of action of load. And the moment generated at a section which is 90 degree away from the line of action of load is F into R divided by 2 multiplied by 2R, that is a centrifugal radius of the centroidal axis, minus pi into R divided by pi R plus L. So these are the moments generated at sections at theta is equal to 0 and 90 degree away from the line of action of load. So similarly, further we will be finding out what is the stresses generated at the inner surface as well as the stresses generated at the outer fiber. I have told you in the previous lecture also. So if it is a tensile load acting here, with respect to section BB at inner surface, it is the compressive stresses will be generated at inner surface. Compressive stresses will be generated, and at outer surface, tensile stresses will be generated with respect to section BB. Whereas with respect to section AA, due to tensile load acting, it will be tensile stresses will be generated at the inner fiber and compressive stresses will be generated at the outer fiber. So the same condition will also exist here. Okay, so we'll go through a problem where we'll be using the stress equation as well as these moment equations, and we'll calculate the stresses generated at the inner as well as outer surface. We'll not be going through a derivation. We'll directly straight away go to a problem. This is the problem which is mentioned here. So a chain link, they may not give you the figure, so you need to know the figure, and the figure is also present in figure 10.3 in page number 160 in your design data handbook. Okay, it is also already there, so you can refer that. So a chain link made of 40 mm diameter. So chain link is having a diameter of 40 mm and it is semicircular at each end. So it is semicircular at the top and semicircular at the bottom. Let's say it is at the top and bottom for now. Okay, and it is having a diameter 40 mm. So it is a circular cross section in general. So the mean diameter of which is 80 mm. The mean diameter, that is the diameter which we can consider here, is around 80 mm, and if the link carries a load of 90 kilonewton, that is F is around 90 kilonewton, what estimate the tensile and compressive stresses in the link along the section of load line. Along the section of load line we have to calculate, that is at section BB. We have to calculate at section BB, which is along the action or section of load line, and also find the stresses at a section 90° away from the load line. So we should also calculate the stresses which is 90° away, that is at section AA also you have to calculate. Okay, so the similar procedure we have to follow as in the case of a closed ring. Okay, so as usual, the first step you have to do is draw the critical cross section. So I'll go through it fast. So this is a circular cross section here, as it is mentioned in the problem. Sometimes they not give you the chain link figure and all. You must figure it out, and you can refer the data handbook for the figure. So it is a circular cross section. Okay. So with respect to circular cross section, you draw the centroidal axis. You draw a centroidal axis which passes through the center of the circular cross section. So we will consider the circular cross section which is shown here around here, approximately here we will consider. Okay, so centroidal axis is drawn. So after that you have to draw the neutral axis. Neutral axis will be shifted away from the centroidal axis since it is a curved beam, and neutral axis will be shifted towards the inner surface. It will be shifted towards the inner surface, and distance between neutral axis and centroidal axis will be given as eccentricity E. Distance between neutral and centroidal axis is given as term E. And it is already given the remaining terms, that is the center of curvature. Okay, so this is the center of curvature, and with respect to that point you can draw the center line of curvature CL. CL you can draw, and also you can note that the load is also acting on the same direction or in the same line, right? It is also acting along the center line of curvature itself, that is load is acting along the center line of curvature. So both will have the same position or same line, CL as well as F, right? Next, you can see in the problem they have given the chain link is made up of 40 mm diameter. So the diameter is 40 mm. The diameter is 40 mm, and they have also mentioned the mean diameter of which is 80 mm. So this semicircle which you present here, so the mean diameter of that semicircle, if you consider, it is 80 mm. It is 80 mm. So if you consider the radius, that is from this particular point till this particular point, it will be 80 mm, right? Diameter from this particular point till this particular point, it will be 80 mm. So radius will be from the center line of curvature till the centroidal axis. From the center line of curvature to the centroidal axis will be the radius of the centroidal axis, which will be diameter divided by 2. So 80 divided by 2, it will be 40 mm. So you can see here the radius of the centroidal axis from the center line of curvature to the centroidal axis will be 40 mm. So radius of centroidal axis you can mark it here, and from the center line of curvature to the inner surface will be marked as Ri, and from the center line of curvature to the outer surface will be R naught, right? R naught will be the radius of the outer surface, and Ri will be the radius of the inner surface. Okay, next there is neutral axis. So radius of neutral axis from the center line of curvature can be marked as R subscript n. This is R subscript n. Okay, so the diameter is 40 mm. You can equally divide it, that is with respect to centroidal axis it will be from here to here you can mark it as C1, and from here to here you can mark it as C2. It is 20 mm and 20 mm. So C1 will be equal to 20 mm and C2 will be equal to 20 mm. So those are distances from inner and outer surfaces with respect to centroidal axis. And also you can mark the terms Ci as well as C0. Ci is the distance from the inner surface to the neutral axis, and C0 is the distance from the outer surface to the neutral axis, right? Ci is the distance from inner surface to the neutral axis, and C naught is the distance from outer surface to the neutral axis. This is the critical cross section that you have to draw, right? So next we will write down the data which is given. So the length of the straight side is given as 80 mm, okay, and the diameter, mean diameter, that is diameter with respect to centroidal axis, is 80 mm. Diameter with respect to centroidal axis is 80 mm. So radius of the centroidal axis will be equal to 40 mm. Radius of the centroidal axis will be equal to 40 mm. Right? This we have already discussed, and the load acting here will be around 90 kilonewton. So it will be, write it in terms of Newton itself. Write it in terms of Newton. So mean diameter with respect to centroidal axis is given 80 mm. So radius of the centroidal axis will be 40 mm. So you can take it as R or capital R, because in the data and book formulas it is given as capital R. So it is nothing but capital R itself. Okay. So after that, diameter of the link, you know, it is around 40 mm, right? It is 40 mm. So I have already said from here to the centroidal axis distance is nothing but C1, and C1 is equal to 40 divided by 2, that is 20 mm. So if you know centroidal radius, that is radius of the centroidal axis, if you know RC, and also if you know C1, that is C1 equal to C2 equal to 20, right? So if you also know C1, then RC minus C1 will give you inner radius of the curved beam. It will give you inner radius of the curved beam, that is 40 RC minus C1 minus C1, right? C1 is equal to 40 divided by 2. And outer radius of the curved beam is simple. So if you know centroidal axis, right? If you know radius of the centroidal axis plus C2. C2 is equal to C1. So RC plus C2 will nothing be equal to 40 divided by 2 plus 40. 40 is the radius of the centroidal axis plus C2, which is 40 divided by 2. So outer radius of the curved beam also you can calculate. So this is what I said, C1 equal to C2 is equal to 20 mm. Next, the one radius which is missing is the radius of the neutral axis. You might be already familiar. This is the third time we are using this equation, which is for a circular cross section from table 10.1 in page number 162. Okay, so C is nothing but C1 is equal to C2, that is the C value, and R is the radius of the centroidal axis. So you substitute. So carefully do the calculation. So the radius of the neutral axis which you will get will be around 37.31 mm. So next we'll calculate the remaining parameters which we have to find out. So one is the distance from the centroidal axis to the neutral axis, that is term E. So E can be given as radius till the centroidal axis is known and the radius till the neutral axis is known. So RC minus RN will give you the value for E. Will give you the value for E. That is obtained here. So 40 minus 37.371 will give you 2.69 mm. So the remaining things, that is same procedure, distance of neutral axis to inner radius, Ci can be calculated. So if you know radius of the neutral axis, and if you reduce inner radius from that, Rn minus Ri will give you the Ci value, that is distance from the inner surface to the neutral axis. And the distance of neutral axis to the outer radius can be calculated as whatever is the outer radius, the entire outer radius minus whatever is the radius till the neutral axis. Whatever is the radius till the neutral axis. So remaining distance which you calculate will be for C naught. So if you know diameter, you can reduce diameter by 40 minus Ci, if you will get C naught also. That way also you can get C naught value. Next you find out the area of cross section. For a circular cross section it is pi by 4 d square. Substitute d, that is 40 mm. So you can get the area of cross section. Next, as usual, similar to the previous procedure on closed ring, we'll consider two sections. First, we'll consider the section BB. Which is at theta is equal to 0, acting along the line of action of load. Right? So with respect to section BB, we will calculate next the direct stress, then the bending stress at the inner fiber as well as at the outer fiber, and we calculate before that we calculate the moments. We'll calculate the moment and then the bending stress as well as the combined stress at the inner and outer fiber with respect to section BB. After that, the same procedure will follow it for section AA, which is 90 degree away from the line of action of load. So at section BB, first where it is theta is equal to 0, so direct stress acting will be positive. Why it is positive? Because it is a tensile load that is acting here. That is why direct stress will be positive in nature. So F value we already know, right? And area we just calculated, and theta is here equal to 0. Theta is equal to 0. So at section BB, direct stresses which will be acting will be completely 0. No direct stress will be acting at section BB. Only we have to calculate the bending stress. So for bending stress, first we have to know the bending moments that is acting at section BB where theta is equal to 0, right? So you can get this formula, that is which is present in a section page number 159 in equation number 10.2b. 10.2b. Carefully read it. Carefully read it. So this equation which you have considered is for a bending moment at section BB, that is at the point of application of load. Read the description given in equation 10.2b in the data handbook. Bending moment at the section BB, that is at the point of application of load. That's why we consider 10.2b equation for section BB, right? Which is because it is acting along the line of action of load. So substitute the force value as well as the radius of the centroidal axis value to this bending moment equation, and the resulting value will be the bending moment value acting at section BB, which is around 1.40 into 10 to the power 6 Newton mm. Okay. Using this moment, further we will calculate the stresses that is generated at the inner as well as at the outer fiber. And I have told you previously also, so the whatever moment is generated at section BB due to tensile load acting, it is basically the compressive stresses are generated at the inner fiber and tensile stresses are generated at the outer fiber. Okay, tensile compressive stresses are generated at the inner and tensile stresses are generated at the outer surface. So we'll calculate one by one. Okay. So first we'll calculate the bending stress at the inner fiber, which is from equation 10.1b in page number 159. So be careful, as I told you, at the inner fiber it is the compressive stresses which will be generated. It is the compressive stresses. So first section which we consider is acting along the line of action of load. So for that particular section, it is the compressive stresses at the inner fiber. So it will be negative in nature. It will be negative in nature. This negative is not there in your data handbook, but you have to put it here because it is the compressive stress. And same formula will later maintain also. Okay. So moment value you know, CI value you know, A, E, RI also know. Substitute the values and calculate the bending stress generated at the inner fiber, which is minus 358.45 Newton per mm square. As it is negative, it is a compressive stresses are generated at the inner fiber. So once you calculate the bending stress at inner fiber, you can calculate the combined stresses which are generated at the inner fiber. So combined stresses will be sigma is equal to whatever direct stress is generated plus the sigma BI value, right? It is already negative, so combined stresses also will be a negative value indicating the compressive nature, right? So these are the same procedure. Combined stress at the inner fiber we will calculate. Next we will consider the bending stress at the outer fiber. Bending stress at the outer fiber we will consider equation 10.1c in page number 159. In page number 159. So as you can see here in the equation in data handbook, there it is negative, right? But we can't consider negative here. Why? Because at the outer fiber it is tensile stress that will be generated here. at the outer fiber, it is the tensile stress that will be generated here. So we can't consider negative here, it should be positive. It should be positive value. So sigma B naught is equal to MC naught by AER naught. So substitute the outer radius, distance of the outer fiber with respect to neutral axis as well as the bending moment you substitute. So you can calculate the bending stress at the outer fiber, and it will be positive value which indicates the tensile nature. So once you calculate the bending stress at the outer fiber, next you can calculate the combined stresses that needs to be calculated with respect to the outer fiber or the outer surface. So sigma B naught, naught is equal to sigma D plus sigma B naught. So sigma D is already 0. So stress at the outer fiber will be sigma naught, which will be a tensile stress, which will be a tensile stress, right? So we completed calculating the bending as well as combined stresses at the inner as well as the outer fiber. We have completed the stresses at the inner as well as the outer fiber. Next we'll go ahead and calculate the stresses that are generated at section AA. At section AA, which is 90° away from the line of action of load. So first step what we have to calculate with respect to any section is the direct stress. So since tensile load is acting, so the direct stress will be a positive value. But here direct stress won't be 0 because the direct stress which we are considering is at a section which is at 90° away from the line of loading. So since that is the condition, there will be definitely some amount of direct stress that will be generated, and theta is equal to 90°. So the direct stress generated at section AA will be around 35.81 Newton per mm square. Okay, it will be around 35.81 Newton per mm square. After that, the next step is at section AA we have to calculate the bending stress. Before that we need to calculate the bending moment. So bending moment, you can refer equation 10.2a in page number 159, right? And there is a small, this line is missing in the equation. Okay, there is a printing error, this line needs to be there. Okay, and you can read out the description given in equation 10.2a. It is the bending moment at the section AA which is 90° away from the point of application of load, right, and in all the straight parts of the link. So it is 90° away from the line of action of load. That is the bending moment equation which we will be considering at section AA. So substitute the load as well as the radius of the centroidal axis value, and the resulting moment value which you get is a negative 1. Is a negative 1. So this couple actually produces tensile stress at the inner fiber and compressive stress at the outer fiber. If you observe, this couple will produce tensile stress at the inner fiber and the compressive stresses at the outer fiber. Okay, it is tensile stress at inner and compressive stress at the outer fiber. So we'll go ahead and calculate the bending stress at the inner as well as outer fiber at section AA. Okay, as I repeated, you can refer to equation 10.1b for determining the bending stresses at the inner fiber, but we will maintain the same equation which we considered earlier for section BB, which will consider the same equation which we considered for section BB in our previous case. The same equation we'll consider here itself. Why? Because the moment value which we calculated is negative. So negative into negative, it will end up with positive. So the bending stress at the inner fiber is tensile. So we'll get positive value only if we consider the same equation. So substitute the moment value which is a negative 1. Substitute the inner distance as well as area, eccentricity and radius of the inner surface. So the resulting bending stress at the inner fiber will be a positive value which will be tensile in nature. Okay. So this is the bending stress at the inner fiber. Next you can go ahead and calculate the combined stress at the inner fiber. So sigma d value is already there. Sigma is equal to sigma d plus sigma bi. Sigma d value we have calculated, which is around 35.81 Newton per mm square. So add up with the bending stress at the inner fiber, you will get the combined stress, which is a tensile stress, which will be generated at the inner fiber at section AA. This is the final combined stress which you will get with respect to inner fiber. Right. Now we will go ahead and calculate the bending stress that is generated at the outer fiber. Inner fiber, it's completely done. Now the final remaining calculations with respect to outer fiber is remaining at section AA. So same equation which we previously considered in our previous case for section BB, we'll consider here. That is the positive case we'll consider. Why? Because moment is negative. So when you substitute, the stress generated will be a negative value indicating the compressive stress at the outer fiber. So we'll consider the same equation and substitute the moment, distance with respect to outer surface from neutral axis, area of cross section, distance between neutral and centroidal axis, and the radius of the outer surface. You can substitute all the values. After careful calculation, the bending stress at the outer fiber generated will be minus 44.711 Newton per mm square. It is negative, indicating the compressive stresses which is basically generated. So once the bending stress you have calculated, once you have calculated the bending stress at the outer fiber, and finally you can calculate the combined stress at the outer fiber, that is sigma naught is equal to sigma d plus sigma b naught. So sigma d you know, and sigma b naught is a negative value. So the stress at the outer fiber will be minus 8.901 Newton per mm square, which will be compressive stress generated at the outer surface. Right? It is the combined stress at the outer fiber. So we have calculated the bending stress as well as combined stress at the inner as well as the outer fibers with respect to section BB, which is acting along the line of action of load, and also at section AA, which is perpendicular and 90 degree away from the line of action of load. So these are the calculation which we have to do in this particular